So hello everybody. Today again, this is the lecture number 5, I guess, in the series of mechanics for GATE 2026. Okay, and today we are going to discuss some practice problem. Okay, so first I have taken some objective questions. These are the very conceptual point of view. So I have taken that, and afterwards I have taken 4 PYQs question from GATE, and we will solve that only. Okay, so let's start. Though so the first question says concurrent forces in a plane will be equilibrium if so in a plane means all the forces should be in one plane, whether it should be in xy or yz or anything. Okay, and concurrent means it should be based on only one point. Okay, so let's suppose it's based on the origin point only x. Okay, sorry, o. So let's suppose three forces are there, f1, f2 and f3. Okay, and so what the question says, concurrent forces in a plane will be in equilibrium if. So how all of them can be in equilibrium? So the options are given. Some of the forces is zero. They are just saying that algebraically, like we will just add it f1 f2 3, and if this all gets to zero, then it is in equilibrium, but that's not the condition. Okay, and the second is algebraic sum is zero, means same almost saying the same cases. I think so the sum of forces is zero here, I mean. So we will count the direction of the forces as well, but that's also not correct. And the sum of the resolved part is zero. Okay, and the fourth option is sum of the resolved part in any two perpendicular directions are zero. That means we will this one is correct answer. Okay, let me explain it. So let's suppose here if f3 is the only force that is not resolved in x, either in x or in y. Okay, so we will resolve that f3 in both x and y, and we will do the addition term in x direction especially, and we will equate it to zero. If it coming zero, then it's in equilibrium in x direction, and when it's coming in zero in y direction as well, then we can say that the equilibrium forces are acting. Okay, because it is in plane, so the summation of the forces of the resolved forces should be zero in two perpendicular cases. Okay, so that's why two perpendicular directions are zero. Even now, if so ki the forces are not coplanar forces, only they are in they are concurrent forces. That means they are in space. So in that case, we have to tick the options where the three perpendicular directions are there. That means the sum of resolved parts in any three perpendicular directions are zero. Okay, so that will be the correct answer in case of a space. Now second question is pretty easy. A free body diagram is the representation of what's the representation of the free body diagram. So it is representation of not a force, actually not. For example, a box is kept on a wall, and if you apply a force here, that means the free body diagram of this body is should have a normal reaction as well and a force as well. Okay, that means a normal reaction, action and reaction, both cases. Okay, so both active and reactive forces. This normal reaction is reactive forces. Okay, and this one is active forces. So both should be add to get that point. Okay, reaction on the body, no, both of them. Okay, neither the active nor the reactive, no, sorry. This two forces representing together in a free body diagram. Okay, now the third question is, when a driver operates the gear shift lever, it is so when a driver operates the gear shift lever. Okay, so it's a couple, that means it's shifting a couple. That's why this gear shift is occurring in vehicles. Okay, now the fourth question is, three coplanar forces acting at a point can be in equilibrium only if. So okay, the same cases which we are discussed in the first question, but here it is discussed in a space, I guess. Three coplanar forces, sorry, they are in a plane only, are acting at a point can be in equilibrium. That means let's suppose three forces f1, f2 and f3. Okay, and they are acting at a point. Okay, that means the point is O. Okay, so they are all acting at a point. So it's asking that they can be equilibrium in what cases. Okay, so all three forces are parallel. No, if the all three parallel forces are parallel, then the net forces would be summation of all the forces of F1, F2 and F3. Okay, so that's not be equal to 0, and that might be case that they might not be 0. Like for suppose they can be 0, obviously F1 is there, a double of the magnitude of F1 plus F2. Okay, and opposite forces are acting F2 and F3. This can be 0 if F1 is equal to F1 plus F2. Okay, sorry, F1 is equal to F2 plus F3. So this is a particular case, right? It can't be possible in every scenario. That's why all the three forces are parallel, may not be true always. Okay, the all three forces are concurrent. It is obviously concurrent, so it's also not true. All the three forces are parallel or concurrent. Okay, okay, so that means ki these forces like F1, okay, F2 and some F3, this can only be equilibrium in this case only, right? Because the moment is also getting 0, but in this case the moment never should be equal to 0. That's why it's not a always case, it's a particular case. But this one is always case, like whenever F1 is equal to F2 plus F3, then it getting equal. All three forces are aspasial. No, it's a coplanar forces. This option automatically gets cancelled, so the correct option only here remains is C. Okay, so the fifth option is Lami's theorem gives the following when three concurrent forces acting on a body kept in equilibrium. Okay, so this one is we have studied that. Yeah, option is D. Let us explain it once again. F1 is here, F2 is here, sorry, F3 doesn't matter, F3 2 is here. So if any angle theta 1, that's opposite of F1 is theta 1, just opposite of F2 is theta 2, and opposite of F3 is theta 3. So according to Lami's theorem, F1 is sine theta 1 and F2 is sine theta 2 and equal to F3 sin theta 3. Okay, we have studied this one. Actually it is a case says that these all three terms are constant. Okay, so there is force is proportional to the sine of angle between the two. So this term is constant, that means F1 is constant multiplied by theta, that means F1 is perpendicular to theta 1. Okay, so that's option is correct. Okay, so this is direct a straightforward question, nothing to think about any options. Okay, so I directly told the answer there. For a particle to be in, I'm going to sixth question. For a particle to be in equilibrium under the action of two forces, the forces must be, so it's saying like for a particle to be in equilibrium, any particle is given, it should be in equilibrium under the condition of two forces. Okay, so like two forces are acting, the forces must be what's the condition so that the body is in equilibrium. Okay, concurrent and parallel. Okay, that means a force is acting here, let's suppose this body. So this I'm discussing here the first case. Okay, so F1 is acting here as well, and parallel means and again another point, another force is acting at the same point in this direction F2. So if we sum of this, keep the sum F1 plus F2, this never would we get to 0. Okay, so this is not equilibrium case, so this option is not a correct option. Unequal non-current, non-current, that means it's saying that F1 is acting something here, unequal and unequal non-current, sorry, that means they are not acting at any point. So suppose F1 is acting here and F2 is acting here. Okay, non-parallel, unequal and non-current. Okay, these forces are not equal and not current as well. Concurrent means they are not acting at same point, and in magnitude wise they are not equal. Okay, okay, that means the summation is also not getting 0. Okay, and we can see that directly here, right? Some component will get discovered here, F3, which will be the sum of F1 and F2. Okay, and the direction will come as a vector sum. Okay, now we will see the option number C, equal parallel non-collinear forces. That means two parallel forces are there, F1 and F2, and they are equal. Okay, so again since they are parallel, so the again sum of them two will not be equal to 0. So it's not a again not a equilibrium case. So the fourth option is correct, equal, opposite and collinear. Those are so simple equation. Like see, F is acting here as well, F is here acting as well, and they are both acting at a single point, that is collinear, opposite in nature and equal. So it is a zero equilibrium case. Okay, now we will see option question number 7. The number of coplanar forces will be in equilibrium when okay, so coplanar forces are there, that means we have to deal in a plane. Okay, plane x and y. Okay, so what you need to do first, for force equilibrium you will do is fx should be 0, fy should be 0, and mx should be 0, and my should be 0. Okay, okay, now in the first question fx and fy is 0, it is only talking about f1 and the forces term only, not the momentum term, so it's also 0. It is dealing with something momentum into force, it's also not correct. Only forces in direction, so it's not correct. This can be only correct, they are supposing to combine both of them to be 0. Okay, that's why this one is 0. Okay, sorry, my bad. This momentum is only one term only in z direction, right? If you do this, momentum can be possible in clockwise or counterclockwise, and this can only come in z and minus z direction. Okay, so only one momentum term will be there, so it's correct option. Okay, it's correct option. Now question number 8. Two cylinders having diameter 50 and 100 mm respectively are held in a container. Bigger one at the bottom and the smaller one at the top. Container has a width of 110 millimeter. What will the reaction at the point of the contact of bigger cylinder to the container wall, neglecting friction? Width of the small cylinder is W, and the width of the big cylinder is 2W. Okay, so I mean, two cylinders having different diameter 50 mm and 100 mm respectively are held in a container. Okay, so let's say a container is there. Okay, two means first one is, I will draw with a different fan. 1 second. Yeah, let's suppose bigger cylinder is this one and the small cylinder is this one. Okay, this is having 100 mm diameter and this one is having 50 mm diameter, right? Yeah, it's really in container, bigger one at the bottom and the smaller one at the top. Container has a width of 110 millimeter. Okay, that means we are talking about this container. Okay, that is brown part. Okay, and it is having width of 110 millimeter. What will be the reaction at the point of contact the bigger cylinder to the container wall, neglecting friction? Width of the small cylinder is W, and weight of the small cylinder is W. Oh, that's why I'm getting confused why it's happening. Okay, so let's suppose this one is grounded person, so W is acting here, and again W is acting here. Okay, I mean 2W is acting here. So what will be the reaction at the point of contact of bigger cylinder to the container wall? Okay. Okay, so let's, this question, I guess it's from some other topic or what. Don't worry, we will discuss this in the next lecture, I guess. Let's see what is the reason. Yeah, this question is from the trusses part only. Okay, we will discuss it there. Okay, and the question number 9, we will move it to there quickly. The resultant of coplanar non-concurrent forces constitutes. So the question is asking the resultant of non-concurrent forces, means the forces which are not in a line. Okay, so it constitutes what? So it constitutes movements or couple. Okay, so the I mean these questions is not a correct way. Yeah, it's correct. Like moment is given, right? So it's saying that two forces F1, some other forces F2, if both are there, they constitute a moment. Okay, if they are both are parallel, I mean opposite in nature and parallel, then they constitute a couple. Okay, and they should have been equal and opposite sorry, equal magnitude. Okay, we have discussed this in the previous lectures. Okay, now turning to the cap of a fan is an example of what's an example of moment, force, couple, impulse. Okay, so ideally it should be case of couple, but most of the time we used to say that it's a kind of movement as well, right? If a pen cap is there, let's suppose you are applying two fingers, so from the one finger, most probably from the thumb, you will apply most forces than the other fingers, right? So for a couple there should be equal and opposite forces. So the forces that you are applying from the two fingers may not be equal. Okay, that's why these two are couples. Okay, no, may not be couple always. Okay, it can be movement. Okay, so both options A and C. Okay, now we will solve some previous year questions. So the first question here is if point A is in equilibrium. Okay, so the point A is here, and it is saying if point A is in equilibrium under the action of the applied forces, the value of tensions TAB, TAC are respectively. So we have to find the value of TAB and TAC. Okay, so we will simply just resolve the forces in Fx and Fy. Okay, so for our reference, we will take this direction as x and this direction as a y. Okay, so we will resolve the forces. So first we will resolve the forces in x direction. So if x should be equal to 0, so that the point A is in equilibrium. Okay, and the movement along A from all the forces is 0, because all the forces acting at point A, I mean these forces are concurrent forces, so moment is also 0. So in equilibrium we have to deal with the moment as well, but in this case there is no moment acting, so eventually it is 0. So we don't have to deal with this. Okay, so first we will resolve TAC, and TAC will come in x direction as TSA in cos 30 degree, right? Okay, plus T, sorry, not plus, I mean see, so TAC term will come in this direction, but TAB terms will come in this direction. So both are in opposite direction. So we will just equate it. Okay, this should have a negative sign. So in left hand side it is should be in negative sign, but when it goes on the right hand side, it will goes with a positive sign, right? So it will come as cos 60 degree, right? And in y direction, when we will just equate the forces in y direction, it will be like TAB. Okay, sine 60 degree plus TAC sine 30 degree. Okay, and it is equal to 600 Newton. Okay, so from here we can say that TAC cos 30's value is, yeah, cos 30 is root 3 by 2. Okay, and here it is TAB, and cos 60 is 1 by 2, so it will get cancelled. So we can replace TAB with root under 3 times TAC. Okay, so we will replace here, so it become root 3 times TAC. Okay, sine 60 will become 3 by 2 plus TAC. Sine 30 will become 1 by 2 equal to 600 Newton, right? And the overall it will become 3 by 2 TAC plus 1 by 2 TAC equal to 600 Newton. Okay, and it will become 4 by 2, I mean 2 directly we can write it as 2AC is equal to 600 Newton. So TAC is equal to 300 Newton, right? 300 Newton. So TAB will become root 3 into 300 Newton. Okay, yeah. So we have we found out TAB and TC. Okay, so some option. Okay, so here in this case options is not given, but in actual problem option is given. Okay, so don't worry, the answer would be same. Okay, so okay, and now we will see the question number 2. Okay, so in question number 2 they are asking, I mean once again I will just in the question these things are not given, so I'm just okay, yeah, okay. So in the question, a ladder AB. Okay, this is AB, and AB is your ladder. Okay, and weight at 600 Newton is resting at a wall. So since the uh, center of the mass of this ladder will be at the same middle point, so the ladder length will be 5 meter. If you go through the Pythagoras theorem, the ladder length will be 5 meter, okay, and it should act at the middle point. So we are taking 2.5 from A at 2.5 meter from B. Assuming the wall frictions contact at A and B is 0, that means frictionless at point A and B. The magnitude of force P is required to maintain the equilibrium. And in the question, the P forces is acting at this point, okay. So the normal reaction would act on the force, and it would act like NA here. Sorry, yeah, direction I have mentioned is wrong. Okay, yeah. So this one is NA and this one is NB. Okay, so the magnitude of force required to maintain the equilibrium. Okay, so what we will do, we will simply do like, let's see, first we will do the moment equation. I am doing it very shortcut method because in GATE you don't have too much time to solve this. Okay, so we will equate the moment at point B because two forces are acting. Oh, sorry, my battery is not. Okay, just 1 second. I'm just correcting my PC. Yeah, it's working fine. Now see the moment about point B is taken, and we will calculate it as NA should be there, and the length from this point B is 3 multiplied by 3, and it's acting in this direction, right? And the W, another forces, that is W, is acting in this direction, right? So the W cos term will come here, and sin term will have 0 moment because it's passing through the point B only. So we will W cos theta is equal to W cos theta because it is acting in this direction and it's acting in this direction. So both are equal and opposite. So we will just equate it. Okay. And why we have taken the moment point B, I will tell you. See, these 2 points are unknown, right? And if we take this the moment about this point, we have only 2 values to be in the equation, and one value is known and one value has to be known. So we can just directly find out NA from here, right? And if we take some other point, we will have a 2 unknowns, so we cannot find from the single equation. But here only one unknown came here, and we can directly find out we will find out this unknown. Okay, so the NA would be W is 600 Newton, cos theta is 4 by 5 and 1 by 3, right? Yeah. So 200 is here, 5 4 is 20, so 160 Newton is NA, right? Yeah. So am I correct? Yeah, everything is right now. 3 into W cos, sorry, that's what I'm saying. Here as well 5 by 2 will come, right? 5 by 2, yeah, because 2.5 this distance I'm taking. Okay, so it will be 2 at 80 Newton and 400 Newton. Okay. Now you will just equate simply since the ladder is in equilibrium. Sorry, so you will equate the horizontal forces, that means in x direction, to be 0. The only 2 forces are there in x direction, NA and P. Okay, and then should be equal, right? So both are in opposite sense, so it should be equal. So P is equal to NA and NA is equal to 400 Newton. Okay, so overall the answer would be 400 Newton. The required value P is 400 Newton, right? So I hope you are clear with that question. Now we will move quickly, and this is question number 3 here. So a rigid wall of weight 100 Newton is suspended with the help of a string. The ball is pulled by a horizontal forces F such that the string makes an angle 30 degree. Okay, 30 degree here. With the vertical, the magnitude of the force. Okay, so here some tension would be acting, right? And this ball, the ball is here, so ball should be in equilibrium, right? So this angle is 60 degree. So for in equilibrium, we will just equate the force in x direction. Okay, it should be equal to 0. So we will take this direction as a x and the vertical direction as a y direction. Okay, so in x direction we can write as t into cos 60 degree is equal to F. Okay, and in y direction we will write as t sin 60 is equal to 100 Newton, right? Okay, from 1 and 2 we can just divide 1 by 2, sorry, 2 by 1. okay, 2 by 1, and we will get t sine 60 divided by t cos 60, right, and equal to 100 divided by f. Okay, gets cancelled, so it is tan 60, okay, and is equal to f by 100 Newton. So f is coming as, sorry, it is 100 by f. So f is coming at 100 by root 3, okay, tan 60 root 3. So this is our required value, okay. So this is the correct answer for question number 3. It's a, I mean, very pretty easy question, okay. So now another very conceptual question. So this one is a very recent, sorry, I forgot to tell you, this one is GATE 2016 question, and this is from 2024. I mean, very recent from very recent question before, okay. So there is nothing numerical here, just you have to think in a conceptually manner, okay. So a rigid massless tetrahedron is placed such that the vertex O is the origin and the other three vertices A, B, C lies on the coordinate axis as shown in the figure, okay. So we have a tetrahedron here, okay. So this point is O, means the origin point is just coinciding with the one of the vertices of this tetrahedron, okay. Okay, the body is acted by 3-point loads of which one is acting at A, so one force is acting here, okay. So let's suppose we call it as Fa in x direction, right. Another force acting at B along in y direction, right, Fy, okay, sorry, Fb in y direction. Now for the body to be in equilibrium, the third force point acting at a point O must be, okay. So I forgot to mention here, some options are there, like some forces should act at 0, right, to make this body in equilibrium. So where it should act, it should act in yz plane or xz plane on xy plane, okay. So since these two forces are coplanar forces, right, in xy plane, so the third force is also acting in the same plane, that is xy plane, and it should be in somewhere in between x and y. It should not be in y direction or whether in x direction, because ultimately we have to do fx equal to 0 and fy equal to 0. If it will act in fx direction, let's suppose it is acting equally fy but in opposite sense, though it is making summation equal to 0 in x direction, it will not get 0 in y direction, so the body eventually not get in equilibrium. So it should act in xy plane, but neither in perpendicular directions like in x direction or in y direction. It should act in between somewhere, so that we can resolve these forces, and overall the summation of the forces in x direction and y direction should be 0, okay. So the concept here is important, so it doesn't go with that one, okay. Okay, so I hope the questions are clear. I am done with the program here. So from the next mechanics lecture, we are dealing with some different chapters, okay. So the first chapter is over, okay. So till then, keep running and goodbye, okay.